So we have seen, let's revise in fast voltage regulators. So in voltage regulator, we have seen that there are different types of voltage regulators. So in this unit, we have to focus on IC regulator LM317 and 337, out of which 317, LM317 is a positive adjustable voltage regulator and LM337 is a negative adjustable voltage regulator. Apart from this, we have to study switch mode power supply, SMPS, as a third type of regulator. Then with the start, we have seen what is the need of regulator. We have also seen what is unregulated, what the term unregulated and regulated means. We have seen the the block diagram of DC power supply, wherein there are different stages, including transformer, rectifier, filter, and the regulator. And the regulated output is delivered to the load. So AC supply has been converted to DC and then it is stabilized with the help of regulators. We have also seen the different terms involved, like line regulation, load regulation, and temperature stability. So if your line voltage is fluctuating, so change in the line voltage upon change in the output voltage for change in input line voltage is called as line regulation. Similarly, we have seen the load regulation, how to calculate it. We know load minus V full load upon V full load. Okay, so what is a no load condition, what is a full load condition, that also we have seen. Different types of regulators we have studied, why they are called as series and shunt regulator, what is IC regulator, switching regulator. In IC regulator also we have seen that there are fixed kind of IC regulators and variable kind of IC regulator. So some IC series like 78XX and 79XX are used to provide positive and negative voltages respectively. So 78XX is a positive voltage regulator IC, three-terminal IC, and we used to connect the external capacitors here so as to get the proper DC voltage with ripple rejection. So these XX number here specify how much output voltage this IC is providing. Now we have also seen that there must be some difference in the input and output. Okay, if IC is providing plus 5 volts, so there must be minimum voltage of 7.3 volts at the input of this IC. Okay, so for every IC there is some minimum value of voltage that must be there in the circuit diagram so that it will provide. So you cannot drop the input voltage below this value if you want to get the particular voltage specified by that IC to be delivered at the output. So we have seen this two different types, and then we have started LM317. First of all, we have studied the block diagram of LM317. What are the different components, like how this comparator operate, what is this, the Darlington pair, the current limiting resistance, how protection circuitry protect this IC by switching off this Darlington pair when the when the output either load current or voltage exceeds beyond the rating. For extra current, the protection circuitry will make your Darlington pair switched off. Right? Then how the IC is used. So we have seen that the output we connect the voltage divider network, which is formed by R1 and R2. Out of that, R1 is a fixed resistance and R2 is a variable resistance. Right? So by varying this part, you can also vary the output voltage, and this IC is going to provide you the variable voltage. Typically, if you see the specification of LM317, LM337 is another three terminal IC voltage regulator, but it is providing negative voltage. 317 is a positive and 337 is adjustable negative voltage regulator. Let's see some. The data sheet I think I have shown to you. So if you see the important specification of this IC, it is specified in the data sheet that output voltage ranges from 1.2 to 37 volts. So you make it 1.2 volt to 37 volt. And this IC is providing the current of 1.5 ampere at its output. Typically 0.1% is the line and load regulation value. So these are the different important specification of this IC. If you refer the data sheet, you will be able to see the minimum, maximum, and typical values of different parameters of this IC. Okay, so you can download this data sheet from the internet. Then before we move to the next IC of 337, see, the things are similar, only one is a positive voltage regulator, another is a negative voltage regulator. Okay, both are adjustable. I also told you about the pinout diagram. The first pin here, adjustment. Second is this input, and third is the out. Okay, and we have derived the equation for the output. Okay. And also I have shown you how you can use the different diodes. As if in the LM317 you are using the three different capacitors, C1, C2 and C3. Why these capacitors are used? You know, this IC regulator is the block in the DC power supply after filter. Okay. So if this IC is located far away from the filter, then you need to connect this capacitor. If it is immediately, it is followed by the filter capacitor, then no additional capacitor is required. But if it is far away from the filter power supply, then you must apply here capacitor C1. So that input AC part will be removed and this will receive the DC voltage. Then you have capacitor C2 and capacitor C3. So for additional ripple rejection and for providing the smooth output voltage, you are using these capacitors. If you see C1, it will be generally 0.1 microfarad. Value of this input capacitor C1 is 0.1 microfarad, maybe a disc or 1 microfarad tantalum capacitor. It may be also 1 microfarad tantalum capacitor. And this capacitor is of 1 to 1000 microfarad. For removing the ripples from the output, we are using capacitor C2. And to improve the transient response, we are using capacitor C3. Now, when you use these capacitor, okay, you can also use the diodes, because you know there is a property of a capacitor. Once they are charged, they will try to discharge. So we should take care that this capacitor shall not discharge through the low current points of this IC. So if you are using this, you will be providing one capacitor here, sorry, one diode here. So as to, and one diode here, which will provide the path for capacitor discharge. Okay, then now we will move to the further topic of IC regulator. We have also solved one problem, right? We have derived the expression that output voltage is equal to 1.25 into 1 plus R2 by R1 plus I adjustment into R2. We have seen the reference voltage of 1.25 volt is there. Across which resistance? Can anybody tell me? Across which resistance 1.25 volt is present? R1 or R2? Yes, across R1 or across R2?
R2 ma'am.
R2.
कुठे असतं? No, not. This is R1. This is R2. This is R1. This 1.25 volt is developed between adjustment and output. So this is there. And what is between these two? R1 is there. So 1.25 volt is present across R1 resistance, not R2. That is why I told you that we use here some standard value many times, that is 240 ohm. 240 ohm. So remember, 1.25 is the reference voltage which is present between these two terminal, or you can say which is present across resistance R1. Then we have solved a problem also. Okay, now we will solve one more problem based on design. So let us solve one problem of design. Design an adjustable voltage regulator please join in time using, everybody please note down, LM317 for following specification. What are the specification? Output voltage VO is given as 5 volt to 12 volt. What does it means? This is an adjustable IC regulator, so it can provide you variable voltage. So you may have voltage from 5 to, you can change your voltage minimum 5 volt and maximum 12 volt in typical example. Okay, then output current IO is 1 ampere. R1 is given here, or if not given, you can assume. Okay, if R1 is not given, you can assume it. So this is the problem given. So let us solve this problem. What we have to do? Design. When it's a design, you have to find the value of different components which are present in your circuit diagram. So you know it's a very simple circuit diagram for LM317. What is there? There is a IC. LM317 IC is there. Then there is this input terminal, this is output terminal, and this is adjustment terminal. And here you have a resistance R1 which is connected between these two, and R2 is connected. This is forming a voltage divider network. I may draw here or here, doesn't matter. It's a variable resistance R2. This is the bare minimum requirement, and then additionally you can have the different capacitors connected here, connected across resistance R2, connected across output. You can have this different resistors. So you may have this C2, C3 connected. So first of all, design. So see what is given output voltage. VO is given that it is ranging from 5 volt to 12 volt. So 5 volt is the minimum value of voltage this IC can provide, and 12 volt is the maximum value of this voltage that IC can provide. Okay. So you have to find value of R2. Now suppose R1 is not given, you can consider you can assume one resistance. Let R1 equal to 240 ohm. It is given, but if it's not given, you can assume one resistor and find another. Okay. Now is the adjustable current given? It may be given or it may not be given. So either you can say that it is very small and neglect, or you can consider the adjustment value is equal to 100 micro ampere. Okay, so this two things Now first of all, what is the formula of output voltage. What is that? It is equal to, anybody, 1.25 into, yes,
1 plus
1 plus
R2
R2
upon
upon R1.
1 plus R2 upon R1. Okay, so if you are neglecting I address, you will get this term, or if you are not neglecting, then it will be R2 into I address. Now you have to find R1. You have already assumed, you have to find value of R2 such that you will get output equal to 5 volt minimum, 12 volt maximum. So first let VO is equal to, not let, so for VO is equal to 5 volt, first we will calculate this. So what it becomes, 5 volt is equal to 1.25 into 1 plus R2 we have to find, and R1 we have taken as 240 ohms. I'll write here 240. Okay. Plus what is I adjustment I have taken? 100 microampere. So I'll write here 100 into 10 raised to minus 6 into R2. Now you solve this and find the value of R2. So in this case, I get R2 equal to 706.43 ohm. Okay, 706.43 ohm. So I got what shall be the value of R2, so that I will get here 5 volt output. Next again, I will repeat it for uh, output equal to 12 volt. So what I get? 12 volt equal to 1.25, that is V reference, into 1 plus R2 upon, this is 240 ohm, plus 100 microampere into R2. So again solve this and find the value of R2. So in this case, I am getting R2 equal to 2.025 ohm. 0.025 ohm. Okay. So now how shall I select R2? Minimum value of R2 I got this much, 706.43. 706.43. 43, and for minimum input output voltage and for maximum output voltage I got R2 equal to 2.025. Okay, so if you are able to find these two value, your design is almost complete. So you have find it. Now this is a variable IC regulator. So you know R2 is a pot. So what to do? We will select a R2 such that I will able to change its value from 706 to this. Okay, either you can have you there must be minimum resistance 706.43, and you should able to adjust your pot maximum of, up to this is ohm, this is kilo ohm, and you should able to adjust its value to 2.02 kilo ohm. So um, you can select a pot of 3 kilo ohm. Select a pot of 3 kilo ohm. So if you select a pot of 3 kilo ohm means you can make R2 as a 3 kilo ohm pot. Means you can adjust this up to maximum 3 kilo ohm. So when you are selecting a pot, you should select the standard one. Okay, so you can select a 3 kilo ohm pot. Now, if you vary, pot means variable resistance. If you vary and make its value up to this, you will get the output voltage 5 volt. And if you vary in other direction, and it's approximately when its value become 2.025 K, then you can get the maximum output voltage 12 volt. So by varying that potentiometer, you can adjust any value. So in whatever value you want, you can adjust it. You have to change the knob to 706 to maximum this. So and you will able to get the voltage range from 5 to 12 volt of that part. Is it clear? Have you understood this problem? In the design problem, you have to select one resistance and find other. So you can select R1 at, with 240 ohms and find the other value. Now, if this problem you are supposed to solve for LM337, so there will be only one difference that you will be getting the output with minus sign. Okay? So whatever you are solving, give the minus sign at the output, because in that formula you will get this term with minus sign and this term with minus sign. So both minus you can take common and you will get the negative voltage at the output. Have you understood the problem how I solved?
Yes, sir.
So now moving on to the next topic. So the derivation is same, equation is same, but only you can enclose this in a bracket. You can enclose this in bracket and can give minus sign here for LM337. Okay, in the LM337 you can make only one change. So block diagram of LM337 is again same. Its output varies with the negative sign, that is minus 1.25 minimum to minus 37 volt maximum, and 1.5 ampere current you may get. And you can apply the ranges of input voltage up to from minus 3 to minus 40. Rest of the things are the same. It is also providing the short circuit current, short circuit protection. Okay. Now we will see an important concept of current boosting. Okay, current boosting. Let's see what is this current boosting. Current boosting means what? Many times it may happen. You are connecting the IC regulator. Okay. How much maximum, how much current this IC regulator is providing? If you see the specification, you will find that 1.5 ampere current is been provided. Okay, so 1.5 ampere current LM317 is providing. But sometime if you need more current, if the load require more current, then from where shall you bring this current? Because for every IC there is some limitation that it can provide that particular mentioned current in the data sheet. But suppose your load requirement is of more current, so where from shall we bring this more current? So you can have the additional current by using a concept of current boosting. Boost the current, improve the current, increase the current, boost the current. So current boosting. Now how current boosting is employed. So let us understand this. You are familiar with this diagram. This is your IC LM317. Then at the output you have connected this voltage divider network. This is the input capacitor. This is the output capacitor. You may have additional capacitor here. Okay. So this much you are familiar with. This much circuit is known to you. Okay. This is a simple LM317 IC regulator circuit. Is it clear? Are you getting? This is your IC regulator circuit. Now I want to boost the output current. I was to increase the level of output current. So how I will increase it? So for that purpose, I will use a transistor. Okay, BJT. So this transistor I am using now. This is the transistor. Which type of transistor shown here? PNP or NPN? Which is this transistor? PNP or NPN? Look at the symbol and tell me. Hello. Unmute and tell me. This is NPN transistor or PNP transistor? Is it so difficult? You can't identify? You learned transistor in first year. Student, please speak.
PNP.
Is it answer or question? First symbol is for NPN or PNP. First symbol I have drawn here.
NPN.
NPN. The below one is PNP. If arrowhead is inward, it's a PNP. If the arrowhead is outward, it's a NPN. So this is a PNP transistor. Now we will use a PNP transistor such that its collector is connected to the output of IC. Okay. Base is connected to the input of IC. Collector is connected to the output. Base is connected to the input. And now between the input and the emitter, we are connecting a resistor. So here there is a resistance connected. Okay, so this is indicating one resistance connected. So between the emitter and base, we used to connect a resistor. Where is collector connected? At the output, base connected at the input. And this is your input supply now. One which you want to maintain, stabilize. One which you want to stabilize. So this is your input source. You have connected your input source to the input terminal of IC and between ground. Okay. So additionally, you are connecting here a transistor such that between base and emitter there is a resistor. Okay. Now let's see how you get current boosted. How much minimum value of VBE shall be there? VBE किती असायला पाहिजे ट्रान्झिस्टर मध्ये, so that this transistor will start conducting base to emitter voltage? Yes. How much shall be minimum base to emitter voltage? How much shall be minimum base to emitter voltage, so that transistor will start conducting? Don't know? Do you know? अरे माहिती आहे की नाही तेवढं सांगा. माहिती आहे? वैभव वैभव भंडारगे, पार्थ?
No, ma'am.
Don't know? Anybody? Tejal?
0.6 voltage, ma'am.
That's around 0.7, whether it's a silicon or germanium. So minimum it should be 0.7 volt. VB's value 0.7 volt. Okay. So below 0.7, your transistor will not come into operation and it will not become on. And when it's 0.7 volt, it will Q1 start conducting. I mean, this Q1, I have labeled it as Q1. It will start conducting. Okay. Now, for the low current, now I will apply here and I will write the equation. You know one relation in the transistor. What is the relation between base current and collector current? What is the relation between base current and collector current? IC is equal to beta time IB, where beta is the amplification factor, current gain. Okay. Base current is very small, but beta is very high. So you get the output collector current by beta times the small input current. Okay, beta may be from 6 to 600. So a high value of beta. So input current is amplified to the output current, which is IC. IC is equal to beta time IB. Okay. Understood? IC, what is the relation between input and collector current and base current? IC is equal to beta time IB. Remember this important expression. Now, where is our load current? This is the load. So, load current is flowing here. Let's call this load current IL. Okay. Where is the output current? This is the IC. Okay. So, it is providing you output current. IC is providing you output current. And this is the collector current. So, this is collector current. IC. At this point, apply KCL and tell me at node A. Apply KCL. What will be the expression? Apply KCL here.
IL is equals to IC plus I naught.
Correct. So IL is equal to IC plus IO. Fine. What is our IC? It is equal to beta time IB. So I will write instead of IC beta time IB. and this IO. This is my load current, output load current. Now what is base current, IB? Where is base current? Just see. IB, where is transistor? This is transistor. So this is the base current. Okay, so how is the direction of base current? How is the direction of base current? If this is entering, IE, then IC and IB are leaving. So this will be the direction of base current. IB, this is IB. Okay, this is IB. And this is the input current. This is a resistance. The current is flowing through resistance. Let's call it as IR. Current which is flowing through this resistance, let's call as IR. This is IB. And this is the input terminal of IC. So the current which is flowing, let's call it as I in. Now apply KVL here and tell me. Apply, not KVL, sorry, extremely sorry. Apply KCL at this node B. Yeah, please do fast.
IV is equals to IN minus R3. Sorry, IR.
I in form. I in is equal to IB plus IR. So what is IB? Therefore, I can write IB is equal to I in minus IR. I in minus IR, correct? Now I will put this one, this is 2. This output current IO, output current is actually I adjustment current plus input current. Okay. Input current I in for this IC. But I adjust is very small, so we will neglect neglecting I adjustment current. What I get? I in input current is almost equal to output current for this IC. So I can write this equation 2. Therefore, your equation 2 becomes, what is your equation 2? IB equal to I in minus IR. And I in can be written as IO. So from, so let's put this 3 into, so I'll say IB now equal to IO minus IR. Okay. Now what is IR? IR is the current flowing through this resistance. There is a resistance. So IR is the current flowing through this resistance. Where is your VB is present? This is emitter and this is base. So VB is present here. And between these 2 points, there is this resistance R. Okay. It means VB, this voltage is present across R. Barabar? Between these two terminal, voltage is equal to VBE. It means voltage across R is VBE. Therefore, what will be current through R? Current through R is equal to voltage across R upon R. What is voltage across R? VBE. VBE upon R. This is the current. Therefore, I get IB equal to IR. I have find it, so I will write it as IO minus, what is value of IR now? This is 4. Value of IR is VBE upon R. So I'll put 4 in this equation. Okay. Finally, coming here, let's check your output load current. What is your output load current? Is this. Our equation 1 gives the output load current, which is equal to IL, which is equal to beta time IB plus IO. I have just now calculated IB, so I will write beta into what is my IB? IO minus VBE upon R. IO minus VBE upon R plus IO. So if I take IO common, what I get? IL is equal to 1 plus beta what my output current is becoming. IL is equal to 1 plus beta times IO minus beta time VBE upon R. Can you read this? I'll rewrite. The load current IL with this arrangement, the output load current is equal to 1 plus beta into IO minus beta time VBE upon R. Now see, previously our output current was IO. Now the load current has boosted by factor 1 plus beta. If you even neglect this term, beta is a very large quantity, so 1 plus beta times IO, the load current has enhanced by 1 plus beta time IO, and this factor is subtracted. So in all, you can get the output current. What was the output current provided by this IC? It was 1.5 ampere. But with this arrangement, you can make the load current to up to 1 plus beta into IO minus beta time VB upon R. So by a factor of 1 plus beta time, the output current is increased. It is getting multiplied by 1 plus beta. Further, if you want more current, you can use here a Darlington pair as well. So with this arrangement, you can boost the current. Have you understood? I will revise again. This IC provide the current of 1.5 ampere. But in some cases, if the load current requirement is more, then you can boost the current by connecting this transistor at this position. Now your connecting collector is connected to the output terminal, base is connected to the input terminal, and in between emitter and base there is a resistor. So if you relate the input and output current, if you derive this, you will find that output current is 1 plus beta time IO, where IO is the original current provided by this IC. So with the help of this transistor, you can boost the current. Boosting means increasing the current. Understood? Yes or no? Hello?
Yes,
Yes,
ma'am.
ma'am.
Got it? Current boosting. Current boosting means what? Increasing the current. And once you connect this transistor and you find the relation between IL and IO, you will find now, previously it was only IO, now it has 1 plus beta time IO. Okay, so it has been boosted. Now we will see the next concept of low dropout voltage. What is a dropout voltage? We have seen that if you want the uh, output current as per the rating of this IC, you must maintain some input voltage which is specified. You must maintain some input voltage. So this input voltage, if you remember, if you see, if you want output voltage of 5 volt at 7805, you must give minimum 1.3 volt at the minimum at the input. So what is the difference between these two? Output voltage is 5 volt, and for that minimum input voltage you require 7.3 volt. So difference between V in and V out is of 2.3 volt in this case. Okay, 2.3 volt in this case. So this difference is called as dropout voltage. The difference between VDO. What is VDO? Dropout voltage. VDO, dropout voltage, is equal to input voltage V in minus output voltage VO. So for IC, the minimum voltage that must exist between input and output so that your IC regulator will function properly. This voltage is called as dropout voltage. Have you understood what is dropout voltage? This is IC, this is the input terminal, this is output terminal, this is VO and VIN. So the difference that must be maintained between these two is called as VDO. The difference between these two voltage that must be maintained so that this IC will function properly is called as the dropout voltage. Okay. So just now we have seen the example of uh, which I see 7805. So 2.3 volt or 2.5 volt dropout voltage for output to be maintained at 5 volt. But there are some application. Now you are using your regulator in many application, but there are some application like car batteries, where input can drop to very low value. Car batteries means what happens in car batteries, your input voltage can drop to uh, very low value, especially in cold conditions. Okay, but we need the efficient operation of the car. So in that case, how this voltage regulator is going to address this, how the things are possible. So in that case, what is done, a transistor, again we use a transistor. Now let me draw the diagram. Yes. You know, this is your IC regulator. Okay, this is the block diagram of your IC regulator. So here we use transistor Q1. Yes, I try to draw here. This is your error. This is your error amplifier where you used to give the reference voltage to the one terminal, and this goes to the transistor. Now here there we connect a resistance R3. Then we connect here a transistor such that this is, then there comes your R1 and R2. That is, this is your output. So current limiting is also happening here. Now look at this. You know what is, this is input side, and you know what is a dropout voltage. Here there is your input, and here there is an output. So the voltage, the difference between VO and VIN, what is your dropout? VIN minus VO, right? Now in between these two terminal, we have connected a transistor. We have connected here a transistor. Okay, and now what are these terminal? This is collector and emitter. So the voltage which is present between collector and emitter, we call it as VCE. So now if you see, this VCE is nothing but the difference between VIN minus VO. Okay, if this BJT is operated in at the age of saturation, you know, when BJT is in saturation, the voltage between emitter and collector, it is minimum. VCE sat is very small value. It's around 0.2 volt. So if this BJT is operated near the age of saturation, then this voltage will become very low, right? Okay, means our VDO, that is dropout voltage, will become very low. It's around 0.2 to 0.3 volt. It means that between input and output terminal, if I make this arrangement, that I connect here a transistor, and this resistance R3 is connected between emitter and base, then my dropout voltage can drop to very low value. So such applications are needed as what I told you in the car batteries when input voltage is dropping. But for the IC regulator, there is a voltage difference between these two. So in such case, low dropout regulators are used. They are called as LDO, where such arrangements are used. This is called as LDO, low dropout voltage. So today we will stop here. And then in the next time, in the next lecture, we will study SMPs. Very important. Please do not miss. So if you miss any one, then you will not understand other. So block diagram, what is basically SMPS is, it is block diagram and its type we will complete in the next lecture.